continue. Good.
Yes.
Okay. Let's wait a couple of minutes.
I have 75 minutes.
Yeah, but we'll hope they all ask questions so that we are not.
So much I cannot hear clearly unless you walk closer to your computer.
Oh,
But
really?
that's okay. But
Yeah, I know because I'm on a laptop mic.
yeah.
So I don't have the key here to get the actual mic.
So I have to read.
I will make sure I'm
Yeah.
close to here so that. Okay, You want to show your title slide?
No, that's for my course.
Oh, that's a different class. Okay.
Yeah.
Okay.
I was teaching cybersecurity and privacy here
Oh, really?
for a PhD student, and there are only 3 students.
There are only 3 students.
Yeah, so quite unique.
Yeah.
So we have.
Go ahead.
Oh yeah. So it is for our new school of data science. They need the courses running, but they don't have students yet.
Okay, so let me introduce Tianhao. Tianhao Wang did his PhD at Purdue. His advisor was Professor Ninghui Li, but he and I have been working since he was a grad student at Purdue, and now he's a professor at University of Virginia in Charlottesville, and he's. I think just to set up the lecture a little bit, you guys remember when we did the randomized response for the distinct queries? It was only a binary value, but local DP is more general than that. Is when you have multiple values, but the users have to add noise before it goes to the central point. Remember, until now, most of the time, what we're saying is the database goes to a curator, and then when they answer query, they will ask, add Laplace noise or exponential noise. In local DP, you will add noise before the users will add noise before it goes to the central server. Okay, so you don't need it. So Tianhao, take it, and I think if you have questions, I think you might have to relate it to me because this is a laptop sort of mic, and he says he can't hear it very clearly. Okay, go for it, Tianhao.
Yeah, thanks.
Thank you for doing this.
Yeah. So I think Sumesh already covered the differential privacy, and but let me still display this figure here to differentiate from local differential privacy. So differential privacy, you have the trust boundary here.
Can you guys hear?
Okay. Can you hear me?
Now, say
Okay.
something.
Hello.
Okay, Tianhao, use your loud voice here. Okay, that's fine. Okay, go ahead.
Okay. Yeah. So for traditional differential privacy, users just send their data to the server or database, and the trust boundary is here. For local differential privacy, trust boundary is moved to each individual users. So users just send the noisy data and don't need to trust the server or other users. So that's a main difference. And specifically, each user has a value V, and there's a similar algorithm notion A here. And after the perturbation, it becomes Y. We have a traditional differential privacy guarantee. And notation-wise, sometimes we call it a frequency oracle because it gives us the estimation of the count of V. There's just no, I guess there's just no reason why it's called the frequency oracle, but it's just a tradition.
So can you go to the previous slide? Just just 1 second. Yeah, I mean, I think what basically think of A as randomizing the value V for the user before it's sent to the server. And that guarantee basically says that after randomization, your two neighboring values, V and V prime, give you the same thing is bounded by into the epsilon. And I think Tianhao is right, counting, it's easier to think when you get these noisy values in the server, you're just counting how many values of a certain type happen, right? So it's like a histogram on the values.
Yeah, so the notion is the same. It's
Hey,
just
just wait 1 second. I think I locked. Okay. Good.
Oh, so
I'm going to stand here.
Okay. So as I said earlier, the notion is essentially the same, but only the trust boundary is different. So there are some industrial deployment, but those are more back in like 2017 or around that time, when Apple is really pushing this and want to like announce to the users, saying that, hey, I really respect your privacy. But to be honest, nowadays it's less popular because of its poor utility, which I'll tell more later. But in the case of Apple, each user's cell phone is sending their data to the server, and the trust boundary is here, and companies can do this frequency counting or histogram thing to find out what are the popular emojis or words, discovery of new words, such that they can do recommendations better. So local differential privacy has the advantage that the data is randomized before being sent to the device. So the server never sees or receives raw data. But on the other hand, it is very limited in that it can only support very simple tasks, and also with very large noise, which I'll show later. I think so. Marshall just mentioned you have seen this binary setting. It's called the randomized response. Maybe I don't need to go into too much detail, but basically, toss a coin. If it is head, just answer truthfully. And the probability of a head is 50%. And answer if it's a tail, also with a 50% probability, you'll just answer randomly. So there are different versions of randomized response, but essentially you have different probabilities. So for example, if I'm asking, do you have some disease? And if the individual has the disease and toss a coin like this, the probability of from disease to a yes answer is basically 0.70 is 0.75, and similarly we can easily calculate other probabilities. So as I said, there could be different like instantiations of randomized response, but they all boils down to some numbers. And essentially, you need to prove that for any inputs, like V and V prime here, right? So V can be disease, V prime no disease, and any answer Y here can be yes or no. It always needs to be below this E to epsilon. So if you put every possible number there, right? So it could be 75% or 25%. You can see it's always bounded by 3. The ratio is 3, so epsilon is log 3 here. And if we looking into each individual answer, you'll think is really noisy, but the intuition of this mechanism is that noise can cancel out, and we can get insights when we do the aggregation. We aggregate multiple answers together. So to see more illustrative example, so those are the populations with no disease. So the answer yes with 25%, and the answer no with 75%. And similarly for the population with the disease. So let's say those are their answers, and we just factor them. Denote N as the total number of users, C sub yes as the number of yes answers. And then we can have a unbiased estimation. Why we have this it boils down to linearity of expectations, because the expectation of N hat yes is the expectation of the whole thing, and these two are the constant. So boils down to E expectation with C sub yes. And we can calculate this expectation, which is 75% of the number of people with the disease, plus 25% of population without disease. And simple algebra gives you this. Any question regarding this point? I think it's just a simple algebra, right?
Any questions? I mean, we did this in class as well, Tianhao. So.
Okay, good. So Vash mentioned why.
There's a question. Yeah.
When you say you're randomizing data, say for example, a user has the smile emoji as their most used emoji. So when you say you're adding noise to that particular data, does the noise constitute of choosing for a pool of emojis or alternating the statistics? So essentially, how do you randomize that discrete data?
Yeah, so I think what the question is like, the set of emojis is discrete, right? Like I think maybe let's say 50 emojis or whatever. And so let's say, you want to report the emoji, the first one laughing. I think I can answer that. What you do is you have a certain probability of reporting the other emojis as well. Okay. So think about, let's say just take two emojis, right? So if the emoji is heart and this, even if it is the laughing emoji, with certain probability, I'm going to send the heart emoji out. Okay. The idea is think about, oh my goodness, what the heck is going on? Why this didn't happen last time? So then the idea is that the same thing that we did with randomized response, a similar thing you can do, and you can still calculate if there are enough users, what is the frequency of those emojis. So the way I would think about it is, even if your emoji is the first one, with certain probability, you'll send the other emojis. So it's not, think of this as a discrete data, not continuous. Tianhao, you wanted to add anything?
I'm going to move from binary to categorical.
Okay, so he's going to move to categorical. So,
yeah. If we have more than one categories, yes or no, right? So we have like 0 to 6 or any number of categories. what we do is we still toss a coin, but this time it cannot be, well, it can be a fair coin, but to better control the epsilon, we need it to be biased, and those are like one possibility. So just illustratively how you can do this, but it's now we have computers, we don't need those, right? But if you toss a coin with a bias p, which means if it is head with the probability p, we report the true value, and otherwise we report the any other value. Okay, so we use a slightly different notation. So y minus p divided by d minus y, right? Because this is any other value. So we can still prove this. And back to the emoji example.
I mean, so yeah, go ahead. Sorry.
If it's another emoji, right? So V, probability of perturbing V back to V is P, but perturbing something else to V is Q, or perturbing V to some other value or some other emoji is Q. So we need to prove that this is bounded by E to epsilon.
So I think coming back to your question, with this protocol, if it's the laughing emoji, it will be reported with probability P, and every other emoji will be roughly uniformly sampled with mass 1 minus P. Okay, go ahead, Tianhao.
Yeah, we can similarly derive a similar unbiased estimation formula. Right? So previously, we have this. Now we have a very similar formula. And in this case, we have, if we set P and Q to be this, we can prove that this is bounded by E to epsilon, and they add up to 1. Okay. Because P plus D minus 1 times Q is essentially 1. So so the problem.
Let's pause over there.
Yeah.
Can the students think where that unbiased estimate comes from? Think for a little bit. So Q is basically that, which is 1 minus P over the rest of the values. Where did that come from? So I think that would be a good calculation for you guys to do yourself, is that this is basically the generalization of, in some sense, the randomized response for multiple values. But the formula is very similar. So I would derive that if you want to understand it. Okay, go ahead, Tianhao.
So one drawback of this protocol is when D is large, P becomes small, right? So if we take different epsilon values and calculate P for different number of categories, right? So yes or no is D equals 2, but there could be more than 1 if you report your race. If you report your emoji, it could be more than 100 different emojis. You report your, I don't know, some configurations or some very fine-grained information. It could be very large number of categories. Then even if you have a pretty large epsilon value here, so 4 is considered to be a pretty large value, you still only report with very small probability of your true value. So because the probability distribution is you report your true value with a high probability, but but this is divided by d minus 1. So, or if you consider this, that when d is large, p is small. So that makes it very inaccurate when d is large. So how we can handle large domains, or how we can make it more accurate when d is larger. So the first kind of solution is from Google. It's called Wrapper, randomized aggregation of privacy preserving ordinal response. So the first letter of the title. So the idea is to encode the value into a bit string, one hot bit string first, and for each bit, perturb it with a binary randomized response. So yes or no. So sort of the example I gave earlier, right? So disease or no disease kind of example. So the intuition is that each location can only be 0, 1. So D in each location is 2. So no matter how original D, how large is the original D, the new D in each location is still 2. But the sacrifice or the trade-off you have to make is that now epsilon must be divided by 2 because, well, you have 2 locations that are differing. I'll show it later. Another example sort of adopted by Apple is using the local hashing methodology. So basically, you just you compress the data. Okay, so you hash the value. So D is a larger domain, and you hash it into a binary bit. So let's say H of V is the hashed result. It can be 0 or 1. Right? And then you perturb it with a binary randomized response. Well, you can not only give the perturb the bit, you have to also give it the hash function so it can be reconstructed. So you have to also report H. So I'll show more detail later. But the intuition is that the domain size is compressed to 2, but there could be information loss because of the use of hash functions.
There is a question, Daniel. So what Daniel is asking is, what is the distribution of the is there some hash function has special properties or has a distribution, or how did they choose the hash function basically, right?
Yeah, so there is a specific property to satisfy its utility, but for privacy perspective, because at the end of the day, you apply binary randomized response, you will satisfy local differential privacy. So yeah, no.
So I think let me answer that. So I think for differential privacy, hash function can be whatever. But for utility, I think they do need some locality sensitive hashing type things, right? For utility, is that similar things get hashed to similar, close by. Right? Did I answer it right? Do you know?
Yeah.
For differential privacy, hash can be any value. I mean, the proof is actually very similar to the post-processing type proof. H can be any function, in fact. But for utility, what you want is that there are 2 values that are similar. They should have more probability of being hashed together. Okay, go ahead. So I think just one thing that just happened is that the vanilla so LDP was not very good with large domains, and we're just trying to make the domain smaller.
Yeah.
Go ahead.
Yeah, so I think back in 2016, we were puzzled because we see both solutions being adopted in different papers, and we were sort of puzzled which one we should use, right? So they look equally good, but they show some differences when we empirically evaluate them. So what are the advantage and disadvantage of each of them, right? So
By the way, is the scheme clear? They
oh,
both.
I will show more detail about the.
Okay.
Yeah. So first one is a binary local hash scheme. So the original protocol uses something called the shared random matrix. Equivalently is a hash function, right? So we just present it this way, so it's at least to us easier to understand. So the user perturbs the hashed bit, right? So this is V is a ground truth. Sorry, V is a true value from a big domain D, right? And H is some random hash function. And the user will perturb it using binary randomized response with the probabilities PMQ this, right? Because in the binary setting, D is 2, so we have, if we go back to the previous slide, we have a D minus 1 here, but when D is 2, it's just a +1. Then the user reports the perturbed bit together with the hash function. Right? As I said earlier, if you don't report the hash function, you cannot reconstruct. So what the user report is, well, A is still the abstract algorithm to satisfy differential privacy. And the output of Y becomes a tuple of the hash function and the perturbed bit, right? So I just denote, so Y can be any hash function and 0 or 1. So I just denote them as a random hash function and it's not perturbed, it stays. So from another V, the probability of selecting the same hash function and after perturbation, it's reporting the same bit is what, right? Because the two processes are independent, you can multiply them, and this can cancel out, and you are left with this, which is pure Q. Maybe you can take several seconds to understand this.
So basically, I think, correct me if I'm wrong, what it's basically saying is the choice of the hash function, which is basically a random matrix, is independent of this coin toss, basically. That's where this comes from, and this is because these two are the same, and this is because of this, right? Well, you didn't see me, so okay. That's so. This is just proving that it is epsilon dp.
So here, yeah. So privacy depends on randomized response, perturbations, no matter what the chosen age is, right? So for aggregation, I have a for example here. Suppose the domain is 1, 2, 3, 4, and I have a very simple hash function that hashes 1, 3 to 0, 2, and 4 to 1. Okay? Suppose this user's true value is b equals 2, and selects this hash function and report 1. Okay? And the true value is 1. So from the server perspective, the server maintains a virtual histogram of 1, 2, 3, 4, right? And after the server sees this, the server knows, oh, it's 1, right? Then the true input could be 2 or 4. So I increment to the counters corresponding to location 2 and 4. So So this is that, and yeah, this is a more formal protocol. After receiving H and B, increments the counters if this is it. So basically it's just describing this protocol. And what I want to show here is that you still have a very similar unbiased estimation. If you go through the expectation derivation, which is very simple, just a linearity of expectations, you can prove this is unbiased estimation. So this is a protocol, and this is how the server can aggregate and then derive the unbiased estimation. Right? So you still need to tally, right? So previously you just count how many yes, how many no. Now you need to do a little bit more work of hash evaluation and then increment the counters. But the estimation formula is the same.
Any questions about this? Okay.
Yeah, more examples. Suppose this is a hash function. I said earlier, each user can choose their own hash function, right? So I just use a toy example. The hash function is the true value plus their index and mod 2. Right? So those are the 5 users' true values, and their indexes by 1, 2, 3, 4, 5. And their x is 1 or 0, right? And suppose the epsilon is set so that p is 80%. So always first specify epsilon, and then you calculate the p. And then yeah, so then you can perturb it so that 80% of the time the bit is preserved and 20% of the time the bit is perturbed, right? And then each user just report their index as well as the bit to the server. And the server, what the server does is to recover the vector and tally the vectors to derive the final Histogram or a vector of counts, and apply this unbiased estimation transformation to get a estimation of the true counts. So you may think, well, this is really noisy, inaccurate. This is because well, we only have 5 users. If we have more like millions of users, it will be very accurate. Any question?
Yeah, I think one thing is very important to know is that this can work at Google or Apple, because if you see the error analysis, the number of users you would need so that this gives you an accurate estimate is, I don't know how large, but with smaller number of users, I think it's a very noisy answer.
There be something like this in each of the local users' case? Would there be a local privacy budget?
So what she's asking is that in the central DP, basically, if you ask multiple queries, you consume, epsilon is additive. Does the same thing happen here?
Yes. So here we are only considering one query, right? So this is a histogram query. Whatever property we prove in central DP will apply here, including sequential composition or whatever. Yeah.
But so,
Go
for
ahead.
example, like you do one round of this and you compute the histogram. You consume some epsilon. Now you do this again in the morning. You have to have you consume another epsilon. So the basic protocol changes that each of these perturb their value before sending, but all our theory that we did with composition, everything stays the same. Okay. Go ahead.
Yeah, so after more detailed investigation of those different methods, we really have the desire to unify different methods, including so it's not that dark, but this is
Yeah,
a
it's somehow
general.
not showing up.
Yeah, sorry. Well, so basically, I presented the randomized response in the general setting, and the report is basically vectorized one-hot encoding or bitwise bit string setting. I didn't go into too much detail, but hopefully it's clear. And also this hash or people sometimes call it a Hartman matrix because that's a shared random matrix that can serve the purpose of hashing here. So there are essentially three building blocks. They look very different.
Tianhao, are you doing the shuffle model at all or no?
At the end.
Okay, okay. That actually is used quite a bit. So when we get there, okay, go ahead.
Yeah. Yeah. So what we construct in order to better understand the different methods is we view LDP protocol as a voting scheme. Okay, so each user basically is supporting a report that reports some candidates. So suppose these are three candidates, and these are possible reports. I'm only considering randomized response here. In the voting scheme, the report is deterministic, right? So I submit a vote for B. It has to be B. But in a local differential privacy protocol, now it's randomized. If you see I'm submitting a report support for B, more likely it's B, but less likely it could still be A or C. So so a LDP scheme, each user reports with the perturbation and it's randomized. That's for differential privacy because it cannot be deterministic, right? But that's how we view different methods in a unified view. So here we use a randomized response as an example. Output can be more complicated, right? For example, in local hashing, the right-hand side should be the combination of the hash function and the space of the hash function can be super large, as well as the bit, right? So, but there still is a support from a relationship from the right-hand side to the left-hand side. You can see, right? So from a combination of hash function to and the bit, you can still map it back to the left-hand side, like what we did before. This is a support, right? So after I see the hash as well as the bit, I believe 2 and 4 are supported. So so for every local differential privacy protocol, there is this relationship from the support from the report to the candidates, and to satisfy each one LDP, it has to satisfy this relationship, right? So so any P and Q, the relationship has to be P divided by Q is E to epsilon. And this can maximize the absolute value of P when we satisfy epsilon LDP. Yeah, so in the high level, each output supports a set of input values that include the true value with the probability P prime. Sometimes it equals to P, but sometimes it does not. And any other value with the lower probability Q prime. So that's a unified view to instantiate the different methods. If you like offline do the same for like randomized for local hashing or wrapper, you can find the same relationship, but with the different P prime and the Q prime values. So the benefit of introducing this framework is that now, well, each output supports the true value with P prime and any other value with Q prime. We can derive the unified estimation function. While previously we have seen they are very similar, but this put them into the exact same page. They are exactly the same, but only the P prime and Q prime are different. Then the benefit of this is we can have the same matrix for a fair comparison of different matrices. So here we use a variance because these are all unbiased. So variance is the next matrix we need to consider. And we can show it is approximately this value. There is a small term we can ignore most of the time. So we are left with this. And the benefit of having this formula is that, well, now we can determine P prime. Okay, so given any epsilon value, we can translate it into P prime and Q prime. And finally, we can just optimize in the space of Q prime to minimize the variance. And given epsilon and Q prime, P prime is determined. So we only need to optimize.
Let's stop here if there are any questions. So essentially what happened here is you can think of that variance as basically a metric for utility. Because if the variance is very large, you're adding too much noise. And essentially that optimization says, give me the best parameter epsilon so that I minimize the utility. Okay, so that was the advantage of this entire framework. But by the way, Tianhao kept using the term unbiased estimate. Does everybody understand? I don't need to explain it, right? Basically, it says the random variable, the expectation is what you want it to be. So once the estimator is unbiased, then the variance is sort of like the utility, right? Because the expectation is what you need it to be. If the variance is smaller, that is better because it's giving you an answer that is more accurate. And that basically says, give me the best epsilon that actually minimizes gives you the best accuracy. Go ahead.
Yeah, thanks. So with that, we sort of optimize the wrapper and the local hashing. So we call them optimize the unary encoding and optimize the local hashing. So they are both coming from this optimization.
By the way, I think he's underselling. This was one of Tianhao's things they did in his PhD. And I think what was very good was, oh my goodness, I don't know, there's something going on the laptop, is that before this, as you know, setting the epsilon is not easy. And this one gave you a framework so that you can set the epsilon to minimize the utility. I think you're underselling your work, but go ahead, Tianhao.
So let's see how we optimize different things. So in the original wrapper, 0 and 1 are equally perturbed. Right? So stay is a larger probability. Change is a small probability, and you can prove for this case because well, sorry, I didn't. So basically, you need to compare two vectors, okay, and these two vectors are both one-hot vectors. And the difference of two one-hot vectors is at most 2, right? Because the other places are all 0. So you only need to consider the 2 locations. So you have to divide epsilon by 2. So that's why I said earlier is it has to divide by epsilon has to be divided by 2 in the wrapper system there. Because 2 one-hot vectors or one-hot bit strings differ by at most 2 locations. So what we observe here is that, well, 0 appears more frequently than 1. If we perturb them equally, it's unfair to 0, right? Because if we perturb that so that if we perturb them differently and maximize the remain the information in 0, we can maximize the overall information transmitted. So what we do is for 1, we just perturb it with a larger probability, and for 0, we perturb it with a much smaller probability. So 1 is purely random, 0 is mostly preserved. So this is derived from our previous framework. So we have reduced the variance from this notion to this notion. It's not obvious, but if we do some real number calculations, it can reduce the variance by more than 50%.
So Tianhao, one question from me. So it looks like from this table that from utility point of view, the OUE is better than rapport, true?
Yeah.
Okay. I see. So using the hash, the Hadamard matrix-based hash function is much better than the one hot encoding of rapport, right?
No, we haven't got into that. This is still within the one hot encoding.
Okay.
But we just perturb in a different way.
I see.
Yeah. So just a simple modification of the parameters, right? So
Also, this is just the optimized epsilon that you used for actually flipping.
Yeah. So
Okay.
well, so epsilon is a fixed. So we just optimize
The probabilities of how.
Yes. Yeah. So we optimize this Q prime. Yeah, because without that, we don't know how to choose them
P and Q.
differently. Yeah. So we just have an idea. We can do it differently, but how differently, right? So yeah, extreme case is the best. So the second case is local hashing. So the high level takeaway is that the sensitive information is compressed into a bit and then compressed. And during this process, there are 2 steps that cause information loss. One is compression, and the second is perturbation for differential privacy. And our high-level idea is balance between the 2 steps, right? Still by optimizing the Q prime there. And let's see what we do there. So So as I said earlier, so in each LDP scheme, each output will support the true value with a higher probability and any other value with a lower probability, right? So here, what we do is we have more groups. We not only compress into one single group because we think, well, into one bit, into two groups, right? One bit compressing into one bit will cause too much information loss. So we have more groups here, and we can calculate P and Q there. Then we can do the optimization of P, which essentially we are optimizing D prime. Well, yeah, so this is our optimization, and we find out that the optimal D prime is when D prime equals e to epsilon plus 1. Okay, so again, without this, we don't know how many groups we want to use, right? So it can be 2. In the original setting, it can be 100 groups, it can be 4 groups. But with this, we now know, so when D prime is e to epsilon plus 1, we achieve the minimal variance. So essentially, we are doing partial derivation and set the partial derivation to 0, and we can got it. So mathematically, it's not that hard. The more challenging thing is to have this framework. Yeah, so similarly, we optimize the term from this to a new term, and numerically, it can hugely reduce the variance. So the LH is what Apple is using, so we can reduce the variance a lot. Yeah, so a little bit of comparison. DE is a randomized response. Its variance is this. Wrapper is what we call SUE here, and OLH is here, right? This is binary local hashing, and there are some other variants.
So I think just to recap, N is the number of users, right?
Yeah.
D is the size of the domain.
Yeah.
And epsilon is your whatever, the privacy budget.
Yeah.
So basically the communication cost says that how much bits go between the user, like the total number of bits transferred to the server, and that variance is basically the utility of each of those methods. Go ahead.
So know that communication for local hashing, we just use a simple hash function that is indexed by the user index, right? So the user just need to send their index, and the chosen hash function is selected by the index. So that's why
a question for the class. Given this table, let's say you're practically implementing it, given this, which one will you choose? Which column? So think about it. N is the number of users, D is the size of the domain, and that is the utility cost. So which one will you choose? If your company says implement an LDP, otherwise you're fired the next day, which is the column you will go and implement? The pink slip depends on it, as they say. Yes. And what about the utility one? Which utility is better? Remember, variance, that's the variance. So that's the opposite of utility. Variance, large variance means worse utility. So which one? See, I even tried to put pressure on you guys that you get fired still. Come on. I will bring this one Jeopardy music and start playing that. Okay, go ahead.
It's hard to see back here. It's like slower.
But SUE has communication cost that depends on the domain. So imagine if like it's the number of emojis or whatever, huge thing, right? So which one would you implement? Which one would you go for? Yeah, that looks, because I think in general, you don't want somehow to depend on the domain size, because the domain size, right? So this is okay, right? Because even if it's n is what, 1 million users, that's not. So I think the variance, and this variance seems smaller, right? Because there is E epsilon square, so I think it would be this. Yeah, go ahead.
Why would we care less about the user space than the domain size? Like I imagine the domain is usually smaller than the user space.
Is that true? I don't think so, right? I mean, imagine that. So initially, a lot of this stuff. Let's say you're doing keyboard completion. Like I think what Tianhao showed earlier. I mean, the number of words, a number of emojis, I think would be much larger. I think, right? Isn't that true, Tianhao? You would probably prefer the order login communication cost.
Yeah.
And I think this comes down with are you going to do the shuffle model next?
Professor.
Yeah.
Yeah, so I think you will see this will come down. Yes.
So like we also like quick search and we're like there's about roughly a million words. So if you're looking at say
There's only what about emojis and GIFs and all that stuff? In these keyboards, they show all that. So I don't know how many emojis are there. Well, in any case, but yeah, sure. If you're doing small domain size, then you will choose one of the maybe the log D one. But in general, what I've seen is people prefer this kind of complexity cost. Right? Do you know? Am I right? Sort of the.
Yeah.
Yeah, but sure. If your domain it happens to be it's a medical domain, you're just saying what's a patient code or something like that, then maybe the others are better. That's why you will see a lot of different LDP protocols. They will list like what Tianhao is doing, what's the communication cost, what is the utility, in this case it's variance. And then you have to basically make a trade-off choice. Which one is better? But I do want to get to the shuffle model because that's what is used now. So let's go, maybe keep going, Tianhao.
Sure. So I also want to highlight that in practice, typically the users will send in their index anyway. So so this login can be saved, right? So in a practical case, but the server's computational overhead of evaluating all the hash functions could be large. I guess that's one reason why it's called a frequency oracle, because the domain size can be even infinite, like a sentence, right? And they just user just do a compression and send in the bit or just a very small domain value, and the server what they want is just evaluate the hash functions on that particular value. So that's a somewhat like a Oracle query. The server won't do do the hash evaluation on every possible values, right? Because they're infinite category. So yeah. So I want to highlight that. So the communication can be saved, but the computation overhead is larger, but typically not an issue because most of the case don't care about the computation, right? Because it's not real time. It's offline computation.
And Google is paying for it, so we don't care.
Yeah. Yeah, so take away randomized response, larger variance. Optimal local hashing is smaller variance. So if you do the calculation, comparing d minus 2 plus e to epsilon
Also, this
versus
answers one of the questions where it will
Yeah.
depend on the domain size what you're going to use.
yeah.
Okay, go ahead.
Yeah, some experiment. I'll skip this. And
Yes.
the summary, 3 different protocols we optimize. So this is best for smaller domains, and we optimize the other 2, and we reduce the variance. And sometimes people prefer this because it's smaller bandwidth. I guess, is more important than computation overhead. But yeah, it also depends on computation overhead. Maybe incidentally or just or not, they have the same statistical property, right? I guess that can also be explained from the unified framework, right? So once you cast those into the framework, they are equivalent. That's why they have the same statistical property. But they are really trading off between communication bandwidth and the computation overhead. So yeah, I also want to compare randomized response with other mechanism. So for example, Laplace mechanism in central DP. Security Laplace is for central DP, right? So the collector is passive and local DP is not. Privacy, they have the same mathematical guarantee, and the utility. So one takeaway is the utility.
Remember, we did this in class, the utility theorem for Laplace. So the utility is how far you're from kind of the answer. If the variance is order 1 over epsilon, and here here there is square root of the number of users is added there. Go ahead.
Yeah. So this is a standard deviation. It's just a square root of variance. Also, we want to compare with the exponential mechanism. You'll see they are almost equivalent. So exponential mechanism is also, you have a database. It's for central DP. That's different. But ignoring that aspect, you also have some input. You have an algorithm. It will give you an output. And you have the same probability, right?
So basically what he's writing there is we wrote it slightly differently. This was basically the sampling of some utility value. And this is basically just the normalizing overall. He's slightly writing it different. Okay, go for it.
Yeah. So my notation might be slightly different, but it's really similar. But I think the difference comes from in exponential mechanism, you have the 2 here, and you can get rid of the 2 only if the scoring function or whatever function is monotonic. In randomized response, your scoring function is not monotonic. However, you still get rid of the 2. So that's a difference because you have a more tailored proof. But otherwise, if you apply a generic proof like exponential mechanism, you need to sacrifice 2 here. So I want to compare the 2 in terms of mathematical proof. They are very similar, but they have differences. Yeah, for in the remaining time, I will do the shuffle model, but in the end, I only mentioned that. So first, let me
Do you have a
show
slide
some-
on? Do you have a slide on shuffle model?
Yeah.
I want to do that.
Yeah.
Because I
Yeah, I
cover the
have.
shuffle model, so this will give them a. Why don't we do that first and then return to this?
Sure. Yeah, just very brief. So we'll have a traditional centralized DP, right? So single trusted server, one unit of noise. The server has a central view of the data because the server can apply exponential mechanism. They have to compute on the true data first. On the other hand, in the local differential privacy, no need to trust the server. That's a plus. But the minus here is you have to add n units of noise because each user needs to add some sort of noise. And the server does not have the central view of the true value anymore, right? So the server only have the noisy answers. And the multi-party differential privacy is you have like a conflicting party. You have two parties with a conflict of interest. For example, two different companies, they are unlikely to collaborate.
Let me. So we'll do this in kind of detail. Actually, it's one of the reading assignments. So what you guys will do is that shuffle DP. What happens is you all will randomize your data, send it to a central server that you trust, maybe run by EFF Foundation. They will randomly permute it, the data, and then then the protocol starts. Okay, right? Tianhao?
Yeah.
So that's kind of what this is doing. So all the data goes to some server, it will shuffle it, that's why it's called shuffle DP, and that shuffle data will go on. So you have to add less noise in this. We'll do it in great detail. Can anybody give me intuition why? So two scenarios. LDP, all of you guys will take your value, randomize it, send it to the server. In Shuffle DP, you will send it to a server run by what is that, EFF Foundation, whatever that, which is some independent entity. Maybe the government can run that too. And then they will shuffle the values and then send it to Google. Why do you think this is? In general, we will do this in detail. You add much less noise in this than this, right? So that's it's called Shuffle DP, and this is what is actually used now. So like Google has something called Cobalt, Microsoft has something, so on. They do this rather than this. There's too much noise in local DP. So any intuition from the class? Why do you think Daniel first, then Ben?
So I think like with normal DP, the idea was just like if you add randomness, it weakens the link between the outcome and like individual data. I guess this just adds two layers rather than one. So perhaps like each individual layer needs to be less random.
Okay, Ben?
I think if I'm an adversary, I'll get like the local DP, I would know like exactly what to be checking for that. But then with the shuffle model, it has additional uncertainty. Like I wouldn't even in order to access.
Yeah, that's both the answers are getting there. So what I think the idea here is that it breaks the link between the randomized value and the user identity. So think about this, right? Even if you guys send me the random value to Google, I'll say, oh, that came from Daniel, that came from David, that came from Ben. Here, if I randomize, that link is broken, right? And you can, I don't know, do you have, how much noise do you have to add? So remember the standard deviation goes by square root and epsilon. Here, I think the square root n is gone, right, for the histogram.
Yeah.
So there you will, so in some sense, at least for histogram type queries or frequency estimation, this gives you as good almost as this. Go ahead, Daniel.
What if you add more like steps of shuffling? So So there are two non-trivial.
Oh no, but if you compose two randoms, suppose you have a permutation group, you sample a random permutation, but now you sample two random. That's not adding any randomness, right?
It would be like, you know, maybe there's like 3 people, and I trust that at least one of them is honest. So I just every one of them, even if 2 of them.
Yeah. So So I think Ben is getting at some point. So sorry, Tianhao, I'm adding commentary to your talk. Is that there are crypto techniques? The paper is called Shuffle DP without the shuffle, and essentially what you do is you think of that shuffler as a specification of a server, and in fact that. Good thing I assigned it to the reading thing, is that you can shuffle actually by just encrypting and some sort of a Byzantine argument, okay? Which implements the same thing as the random shuffler. So yes, the shuffler is like a kind of almost like a specification what you want. You can do it in a distributed way where there isn't a shuffle. Any other questions? So shuffle DP. So just to, I think before Tianhao gets to finish, I took over his thing. Central DP is still used, I think, in some settings. Local DP is phasing out, but shuffle DP is still used. Am I right, Tianhao?
Yeah,
Okay, I think, sorry, taking over. Why don't you finish?
sure. Yeah, so this is actually the shuffle DP, but the previous one is the more general. So what I call is multi-party DP. So you have to sacrifice in that you need to trust the 2 servers will not collude, but you benefit from adding smaller amount of noise. And this is the shuffle DP. So each user just send it to one server and then send it to another server. So to do that, you do a layered encryption. So you can think of it as a layer, and then Microsoft can decrypt and do some shuffling and send it to Apple. Right, so you still add the LDP perturbation, you add the shuffle decryption and the shuffle here, and you do LDP estimation there. So another more generic approach is a multi-party using sort of secure multi-party computation. I don't know, Sumesh, if you have
No,
covered that.
we have not debated. We'll get to that.
Yeah. So
We do that quite a bit.
Yeah, essentially, conceptually, you can do any computation in MPC. So this is not exception.
I think
So you can do
this is
that.
a very exciting area and a lot of ML people moving here. So who knows what's homomorphic encryption? A little bit, okay. So the idea is the following: and we will. By the way, we will do that. Maybe not exactly what it is. Suppose I encrypt 2 numbers, and I want you to say that, give me the encryption of the sum of those 2 numbers that encrypt. Okay. This, but you only have the encryption values. So there are encryption schemes. The best known is called Palier's encryption scheme, where you can actually compute the encryption of the addition. And then not just addition, you can do other kind of computation, but the complexity kind of goes up. And so that is used a lot now in shuffling and how to implement the shuffler and so on. So we'll do that a lot. Yeah, we're going to do that homomorphic encryption of each bit stuff quite a bit. Okay, Tianhao, I think you do have a conclusion thing?
Yeah. So basically, the upper side is shuffle DP corresponding to this figure. And the
Uh-huh.
lower side is multi-party DP. I think you will cover it later.
Yeah.
So it corresponds to this figure. And there are other applications like frequent random sum mining or others. I didn't have time to cover, but those are all exciting topics.
Okay, any last questions? First, let's thank Tianhao.
Thank you. Thank you for having me.
Any last questions for Tianhao? Okay, thank you so much, Tianhao. It was great.
Yeah, no problem.
Bye.
Bye. So the background is my view in my office.
Oh, that is very nice.
Yeah, yeah,
Oh, that looks beautiful.
yeah.
Is this the new building?
Yes.
Yeah, okay. Wow. Oh, you're showing off, Tianhao. You're showing off. My office has the building of another building being built.
I see.
Okay. Okay, see ya.
Okay, yeah, see you.
Bye.
Bye.